Okay, let's get started. How was the homework? How did it go?
Good.
Went okay? I heard 55 is an issue. Was that what I heard?
That one stumped me.
Okay.
28.
28. Okay, so I'm open to entertaining some of these problems because today's lecture is going to be somewhat short. Not that we're going to get out early, but we have some time here in the beginning to the section on continuity. If you watched the course video, which I know you all did, it's pretty self-explanatory as far as what's happening. All right. So we can kind of take it lightly and just do examples from that section. I don't have to go into too much of the theory. So what I'm going to do is I'm going to start with where we left off last time. I'll address a couple of homework questions, and then we'll move on into 1.5. All right? I have the homework videos completed for 1.5 and 1.6, so the entire week's worth of videos for homework solutions are up, and I'll put next week's up throughout this week. All right? Okay, so we ended with this problem last class, and there was a lot of confusion. And I heard that you watched the videos and it helped.
I don't know what it was, but when you did the first one on the video on the homework, it all clicked.
It all made sense. It probably because when we did this one, it was at the end of class. We had been here for an hour and 30 minutes already, and yeah, and I was going quick. So.
But yeah, you broke it down a lot more.
Okay, well, I'm glad that was helpful to you. All right, so we started with theta going to 0, which would mean 3 times 0 would be 0, and sine of 0 is 0. So we get 0 divided by, and then on the bottom we get 0 again because tangent of 0 is 0. So we knew that already. And so what I had us do in class was peel this thing apart. And I'm hoping that you all are comfortable with that. Yeah, I did 1 over tan, but I broke that one down, right? And it turned out to be what, like cosine 5 theta over 1 times 1 over sine 5 theta. So is everyone comfortable with this part of it up to here?
We also did like 5 theta over 5 theta, right?
Yes, that's where I'm going to start. I just want to make sure we're all okay with up to this point. So when we looked at this, I redid the limit and I said, where are we having a problem? Well, when we plug in 0, we get 0 on top here. And so 0 over 1 is not a bad thing. 0 over 1 is okay, right? That's just 0. And then when we take cosine of 0, we get 1, right? Cosine of 0 is 1. So this becomes 1 over 1. So I'm multiplying those two. So 0 times 1, that's still not an issue, right? That's just 0. But it's this last piece that causes the problem. Because we have something that looks like 1 over 0, and that is undefined. So I said, if we have, what we want to do when we peel it apart is look for the part that's causing the issue. This is the part that's causing the issue. So I need to somehow reconcile the problem. And to do that, I use that sine of junk over junk idea against itself, right? Because I know that anytime I see sine of junk over junk, and two things have to happen, but when that happens, that limit goes to 1, right? Or if it's upside down, it'll still go to 1. So what I did was, I don't know how to say it. I mean, other than we just have to be clever, all right? We have to introduce a 5 theta that we can put on top of this so that it'll look exactly the way we need it. And then you have to do 5 theta on the bottom also. Just because what you do the top, you have to do the bottom, right? That's 1. And then because this is all multiplication, we used this property that allows you to move things around. Anyone know what that's called? Multiplication doesn't matter. Commutative property of multiplication, that you commute means just change the order. So all I'm doing here is I'm changing the order of those two. I'm putting the 5 theta here and the 1 here. That's what I'm doing. So that's what I would do on the next line. I think I'll be a little more thorough today by writing it out. And then 5 theta over sine theta, 5 theta times 1 over 5 theta. And so when we run through this again, and we say, okay, this is going to go to 0, that's okay. This is going to go to 1, that's okay. This is going to go to 1, that's good. We've solved the problem of having the division by 0. But then we realized that we actually created a new problem right here, that we have division by 0 again. And so you might be saying, well, what's the point, right? What's the point of doing this? If we fix one thing, I always envision like a boat, you know, you fix a leak and then another leak pops up somewhere, like, you know, that's what happened here, right? But we have this sine 3 theta over here that isn't even a problem, right? This isn't even a problem, but because we can kind of look at it as sine of junk over junk, we don't have the junk here, right? But that theta that's causing the problem can be moved over there and become part of that sine junk over junk. So I'm kind of going to fix the problem here by using that theta on this one. So my next line would be to move just the theta, not the 5, underneath there. Is that all right? I'm using commutative property of multiplication again. What's still over here?
1/5.
1/5, right? Okay. Now this doesn't quite work yet, because in order for this to not be a problem, we have to have the same thing here and the same thing here. This needs to be a 3 theta instead of a theta. So I can introduce a 3 as long as I do it on the top and bottom. So I introduce, it doesn't matter if I do it down here or down there. I introduce a 3 on the bottom and a 3 on the top. That 3 will slide all the way over here and go in front of that, and then they'll match. The only kind of give and take to that is I'm going to have a 3 stuck out here on top now. And so my last line, really, this is it. I think I'm going to be there at this point, is to have sine 3 theta over 3 theta times cosine 5 theta over 1 times 5 theta over sine 5 theta times the 1/5 that was here already, and then that 3 went over there on the bottom, left me a 3 on top, and that's it. And at this point I can take the limit. So I'm no longer going to need to write the limit. I'm just going to look at what each one of these factors does. So this goes to what? 1 times 1 times 1 again. 1/5, right? So, limit of a constant is constant. Limit of a constant is the constant. So you multiply that all together, you get 3/5. So I hope that that makes a little better sense now. All right?
Just a refresher, how'd you get the when cosine 5 theta over 1?
When theta is 0, right? 5 times 0 is 0. And cosine of 0 is 1.
Oh,
and use,
that's how you got it.
yeah. Look at the cosine function at
So
0.
that's why you didn't have to like put junk over.
That's right. That's right.
1 over 1.
Because it's 1 over 1, that's not a problem. Even if it was 0 over 1, I wouldn't care.
That'd be okay.
Yeah, I wouldn't care.
It's only whenever it's a 0.
That 0 on the bottom, you cannot divide by 0.
And if it's 0 just on the bottom, but a number on the top, then it's undefined.
That's right.
But
That's a
if it's
problem
0
though.
0,
0 over 0, then we need to do, no. 0 over 0 is what we're here, what this is all about. Remember, this problem started as 0 over 0, right? And we had to do all this work to realize, look, we actually get a numerical answer. Okay? All right, now 55, right? And then I heard what, 20 what? 28? Let me look at both of those.
Not exactly.
Let's see, 55. Yeah, 55 is 55. Okay, so 55, let me look at that one first, because that one goes more in line with what I just did. All right? So did I do 28 in the homework?
Yes.
I did it?
Yes.
Okay, so I'm not going to work 28 out again. If you have a problem with 28, just talk to me after class. I'll be happy to clarify. Sine theta over theta plus tangent theta. I remember we had a new faculty member come in a couple of years ago. I won't say who it is, but they're really good. They teach a lot of our STEM classes, and they had this problem. They came to me, they're like, I can't get this limit. Right? So this is a tricky limit. I'm just telling you, it's not straightforward. All right? So let's see first of all what happens. If theta goes to 0, right? Sine of 0 is 0. We get 0 on top. And then we have 0, right? Plus tangent of 0, and of course you need to know tangent of 0, 0. So you get 0 on the bottom. So at this point, we have to do something, right? We can't just say that's it, it's undefined, and then move on. Do you remember me telling you that if you just put this and then undefined on the test, what happens? Did I? I mean, you're going to get nothing, basically, all right, for that. All right, so, Anne, maybe you're thinking this. Maybe you're seeing that sine theta over theta. Maybe you're seeing that right there. Do you see that? And that would be 1, except for the fact that you cannot split this into 2 fractions that way, right? You cannot. Because it's 1 term up here and 2 down here. If it was the other way around, you could do it, right? 2 terms on top, 1 on the bottom, you can split into 2 fractions. But this you can't. So you can't split it, right? Okay. So did anyone get this?
Theta over 1 and then 1 over theta plus tan.
1 over theta. Sine of theta over 1 over...
And then times 1 over...
Oh, you mean like just bring it... Yeah, oh, you mean like split it up into 2. Yes, you could.
That was my first.
Okay, so let's just go with that and see where we go. I think this is what you're saying.
Yes.
All right.
And I changed the tangent into sine over cosine.
Okay, that's fine with me. This is a problem or no?
No.
No, that's not a problem. 0 over 1, that's not a problem. This is a problem? This is the problem. So you have to somehow resolve this. But we still can't split this in 2 fractions. So you went with a good instinct, which is anytime you see tangent and you're having trouble, switch it into sine and cosine, right? We did that a lot in pre-cal. So I'm going to do this. We have to be careful because this is going to be a complex fraction. Okay, I can do that. That's where you're stuck. Good. That's a normal place to get stuck on this problem. Did anyone get this? I mean, I'm sure since it's an odd problem, you might have been able to find something out there.
I used one from Alpha, but it used the differential something, d over dx, something that I've never seen before.
L'Hopital's rule.
I went for
Yeah,
like
we haven't done that yet.
I went for cosine theta over cosine theta, like added cosine theta over cosine theta next to, but I just...
Oh, over here?
Yeah, over here. But
That might actually work, but it might. It might. I'm not going to go that route. What I'm going to do is I'm going to say, look, I know that the problem is that this is going to 0, right? Here and here. And I don't think I'm going to ever be able to get my hands around this piece, right? Like I can't, the whole idea here is like maybe I can do the sine junk over junk thing. And this doesn't have the sign that I would need, right? This one does have a sign. And this part's going to 0, right? But the part that's actually causing the 0 is the top, not the bottom. Because cosine of 0 is 1, right? Sine of 0 is 0. This becomes 0, which isn't by itself a problem. It's the fact that it's the denominator that makes it the problem. So I'm going to try and resolve this right here by making the sine junk over junk. So what would I need to have down here in order for this to be sine junk over junk? Just a theta down there, right? I would love to put a theta on the bottom down here, just underneath here. But I can't just throw a theta in there, right? I can't. So how could I force a theta down on the bottom?
Put the fractions together. Or so theta over theta plus sine theta over cosine.
Theta over.
Or break it up in theta over 1.
I see what you're saying. You're trying to put these two together? You could. Let me try this. Let me just rewrite this like this. 1. Is that okay? Like that? That's the same problem?
Yeah.
Okay. I want a theta down here. So what I can do, whatever I do the top, I have to do the bottom, right? What I could do is I could introduce out here, either here or on the outside here. Let me do it out here. I can introduce, how do I get a theta down here from here? What do I have to multiply?
Theta over theta.
Not quite theta over theta. Good. 1 over theta over 1 over theta. Now just pay attention, because when you multiply this through, the theta needs to be on the bottom, right? If you did theta right here, then the theta would be on the top with the sign. You don't want that. You want a theta on the bottom, yes? Okay, but we run into a little bit of an issue here, because if you multiply this times this, you have to go all the way across, right? You have to go to both terms with this theta, don't you? With this 1 over theta? So let me do that. This times this would be what? Nope, careful. 1 over theta times theta. 1, right? So let me write this down. Limit theta goes to 0. Sine theta over 1 times 1 over, now I'm not going to put the parentheses. This times this you just said was 1. Plus, now when I do the 1 over theta to this right here, it's going to go underneath this sine theta, right? It doesn't go to both because it's multiplication. You distribute over addition, but not to both of these. So I'm just going to slap it underneath that sine theta, which is what I want, right? Theta, and then I still have 1 over cosine theta here. So that's the distribution of this through, right? Now what do I still have on top? 1 over theta, which would have to multiply times the 1, right?
It'll be 1 over theta.
I could just change that to 1 over theta? Is that okay? All right. All right, that's where we are. All right, let's just see what happens. If we take the limit, right now, this is okay, right? That goes to 0? Yeah? This is trouble. 1 over 0. Division by 0, problem, right? But let's see if we've resolved this. 1 plus what's sine theta over theta? 1. 1 over cosine theta, as theta goes to 0, 1 again, right? So this is 1 times 1, which is 1. 1 plus 1 is 2. So this denominator is going to 2 now, right? So I don't have a problem of division by 0 here anymore, do I? But I have it up here. So we spring a leak in a different place. But I think I'll be able to resolve that. Does anyone see what I can do to resolve this 1 over theta? Use the commutative law, or commutative property. How about I do this to help you see it? How about I do this, and then move this, it came from here, right, and it went on top? Let me just put it back out here, like that.
Move it to the underside.
Very good. Move this, look, this is really a theta in the bottom, right? That's really what that is. 1 over theta, right? The theta's in the denominator. Why don't I just take that theta and put it right here? And then that's going to be a 1.
Yeah, that's right. Sine of theta over 1 is 0 multiple.
It is, but when you look at it, what is 1 over theta? It's not, this is what's not equal to 1.
1 over theta.
No.
So how do you get away with multiplying it on the outside?
No, it was 1 over theta over 1 over theta. That is a 1.
Oh, okay.
That is 1, right? But this guy went through and did this. This guy was just sitting there on top. If I put this over here, right? If I put it right next to this one, sine theta over 1 times 1 over theta over 1. I think that's the problem you're having, is like you want to make that be on top, right? Yeah. Okay, go ahead, multiply across right now. What would you get? This times this. And then over 1 times 1, which is 1, which is this, right?
And that's still equal to 0.
And that's still, I mean, that is sine theta over theta. That's what it is. Which will become 1 when we take the limit, right? So this gets slid under here, theta. This is gone. And then you get 1 times, what is it? Let's just write the answer out here. On top, let's see, well, this is what? 1 times 1 over 1 plus, we said this was 1, right? So you get 1/2. It's a tricky problem. Yes?
Can
I hadn't worked this out yet, but what I did was, so I brought it all together and I made it one fraction, and then so I multiplied by the reciprocal, like that, and then I used the commutative property and I moved this theta over here. I
Yes.
just 1 over theta.
Yeah.
But I got 1.
Yeah, no, because when you pull this theta out, you have to introduce a theta down here. Because you factored it out. It's got to come out from both. That's the problem.
All right, cool. Thank
Yep. Okay, we good? Now, look, I just want to show you something with this problem. Now that we've done the whole thing, I just want to show you the approach that I would have taken. I went off of, do you want me to call you Nathan or Mr. Boggs? Nathan. Nathan. I went off Nathan's suggestion, which isn't a bad suggestion, to pull things apart, because that's what I told you all to do, right? Right? But I'm instead going to just rewrite the problem like this to start. And I'm going to have that same mentality that I'd really like to have a theta down here. All right? Okay with that? I really want a theta underneath this sign so it'll turn into a 1. And I'm going to introduce my 1 over theta here. See, I'm leaving it all as one fraction. It's a little easier to see what happens if you do it this way. So watch, what's this times this? Don't say 1 because we haven't taken a limit yet, right? Sine theta over theta, okay? Now distribute. What's 1 over theta times theta? 1 plus, now when I do 1 over theta times this, I can do theta cosine theta like that. And then when I take the limit, what happens? This goes to 1, and this goes to 1, and of course that goes to 1 times 1. And this is going to give you 1/2 right away. Okay? Now I know it's easier to see that now, but if I would have just said, hey, I'm going to come in with 1 over theta, you might have been like, well, why are you going to do that, right? Now maybe you see it's because I wanted to attack that sine theta right there with something. Okay, good. We will start today's stuff. Today is about continuity, right? Continuity.
Wait, did you do 65?
65. Let me see. Yeah, I have time. Limit x approaches 2, a negative 2, sorry. 3x squared plus ax plus a plus 3. And look, I encourage you to ask questions. You definitely need to ask questions. I don't mind answering questions, all right, at all. But I normally won't have a lot of time during class to do this. So in the future, if you have a question like this, please come by my office, text me, right? I told you all about my phone, right? Yeah? I mean, I've used it a few times. It's been pretty efficient. So send me a picture of your work. I'll write down something and send it back to you. All right, so the instructions here says, is there a number A such that this limit exists? If so, find the value of A. So A here is a constant. And I should also tell you that in this book, when you see A, B, C, or D within a problem, and even later maybe R, S, or T within a problem, maybe not so much the T, but if you see A, B, C, or D, or R, S, usually in this class, in this book, that represents a number, not a variable. In other words, A here is a fixed number, but they're not telling you what it is, all right? As opposed to X, which is truly the variable in the problem. So they're asking us, is there some number that I could put here that would make this limit exist? All right, well, let's first try and take the limit and see what happens, right? Let's just do direct substitution, direct replacement, plug in -2 for what? X. Okay, so what would I get? 3 times, what's -2 squared? 4, okay. Replacing X with -2, I would get -2A, and then this A doesn't get replaced, right? So just plus A, and then plus 3 over what is this? 4 plus negative 2 minus 2, which would give us 0. So we have 0 on the bottom. What about on the top, though? 12 plus 3? 15, right? Minus a. 15 minus a, right? So what could a be that would possibly make, well, not possibly, that would make this limit exist? Right now, what if a was 0? Just look at this. What if a is 0? We have a number over 0, right? We have not done that yet, have we? We have not. We've done 0 over 0. We have not done a number over 0. So if a is 0, we still don't know how to handle that yet, right? The only thing we've been working on is if a was what? I mean, sorry, if the thing was what? 0 over 0, right? And then we've had some success. So maybe we can have some success if we can make this look like a 0 over 0 also, which would mean a would have to be what? 15? Let's go for it. Let's see. Let's just try that. Make sense? Let's just try a is 15 and see what happens. Let a be 15. And let's rewrite the limit. 3x squared plus 15x plus 15 plus 3 over x squared plus x minus 2. Now we should get 0 over 0 here, right? We could check it. I think I'll clean it up a little bit before I do any checking. 3x squared plus 15x, what's that, plus 18? Because I can put these together. Okay, x squared plus x minus 2. Now I know right now I should get 0 over 0. Do we need to check? 4, this will be minus 30 plus 18. Is that right? No, 4 times 3, sorry, 12. Yeah, you'll get 0, all right? So you get 0 over 0. But we know how to do these, right? Kind of. In this case, we would get the 0 over 0. This would be bad. And we would try and do some algebra. So since they're both polynomials, in fact, they're both quadratic trinomials, we can try to factor. And I believe that numerator will factor. I'm going to guess that x plus 2 is definitely a factor. And what? I'm guessing that that's a factor. Why do you think I guessed that that's a factor?
Oh, they have to cancel.
Because I know when I plug in negative 2, I should get 0. That's how I knew that. But you should know how to factor this, all right? It might take you a minute, but let's see. This one should be x plus 2x minus 1. All right, that's what this is. What's that factoring on top? Is that right? Does that work? Something ain't right. Yeah, that's it. 3x squared plus 6x plus 9x, which is 15x plus 18.
Is this coming from 3x squared plus 8x or?
It's this one right here. I'm doing this one right here. We good? And now you see the x plus 2's will cancel? So long as you promise me that x is never negative 2, which it's not because this is a limit. And what does the top go to here? Plug in negative 2 to here. Negative 6 plus 9.
That's
3 over, careful, negative 3, and you get negative 1. So we found an a that would make this limit exist. It's 15. Yep. So you see how I did this? I went and I did a direct substitution. I said, hey, look at this right here. I want to force that to be 0 over 0 because that's what I kind of feel good that I can do. And so I said, well, obviously a would have to be 15. And then I went through the actual computation and I did show that the limit does exist that way. A more profound question would be, is that the only a? but they didn't ask that. All right. They're bonus for your brain, yes. They're more information.
It really helps your brain. I think it makes you cry.
I was having a discussion with someone about, why we do this, why we're sitting here doing calculus, and why do you need this course? Are you ever going to be doing these limits? And that's kind of like this age-old question, like, why am I doing this? And what I want you to keep in mind is that this has very little to do with the actual calculus. It has more to do with the way you think, right? I mean, this is just, we're trying to train your brain to think a certain way. And that should help you in whatever path you're going down, A lot of you are engineering, right? Computer science. It's a certain way you have to think to do well in that field. Now, you may talk to someone who's an engineer who's like, I would never do calculus. And I agree, but hold on. What I do promise you is that they can think a certain way. And that only happened after taking more and more classes where they had to just, view problems from a certain perspective. And that's what this is all about. Now, if you're going to become a doctor and they're requiring Cal 2, it's not so much the thinking as it is they need to weed people out. So they up the math requirement. That's a different sort of thing. So, all right, excuse me. Good.
May I interrupt you for a second?
Sure.
I think our internet's a little bug. I think our internet is a bit out of it. Oh, wait.
Oh, that's okay. I don't need it. Thank you for noticing my Wi-Fi bars, though. I appreciate that.
I have ADHD.
It's okay.
I have ADHD.
Oh, no, that's a pretty small little thing to recognize. That's observant, very observant. Yeah, we're not streaming any Netflix right now. Okay, continuity. We need to move on. So for those of you who did watch the continuity section, do you feel like what I was going over in the videos was enough for you to get a basic idea of what's happening? Yes? For those of you who watched it? Okay, so let me kind of quiz you a little bit here. Let's say that we have a function that does this. All right. Is that function continuous at 3? No. Why is it not continuous at 3? Because there's a hole.
Isn't that a removed continuity?
This is called a removable discontinuity. Because to fix it, all I would have to do is come in here and define this right there, and then it would be continuous, right? All right. How about this? Hold on. Let me finish drawing it.
Sorry.
Let's say 3 again. Is this continuous at 3? No? I agree. It's not continuous at 3. But it is, okay, it's a jump discontinuity. It's not continuous at 3, but there is some type of continuity we have. What is it called? Right continuity. So this means that as we come in from the right, we are headed to the value of the function at 3. So this would be right continuous, but not left continuous. And then if I switch it around, right, and do this, that's a bad marker. This would not be continuous at 3, right? But it would be left continuous at 3. So, I mean, that's like the basic idea, and I hope that the video, illustrated that pretty well. What we want to do today is we want to do some examples, all right? Because you need to know like how you're going to use this, right, on a test. What are the problems you're going to be asked? But you have to have an idea of what we're doing first, right? Like what the picture is. I say in the video that the main idea behind continuity is the idea that you can draw a function without picking up your pencil. If you can draw a function without picking up your pencil, then your function is continuous. While you're drawing, it's continuous. As soon as you pick up your pencil, you have a place where you're discontinuous. And there are 3 types of discontinuities, right? 3 types. Where are all these bad markers coming from? 3 types of discontinuities. What are they?
Jump.
Okay, first one is a jump. And a picture of this would be any graph that at some point has a break in it. Doesn't even matter if it's defined, if it's left continuous, right continuous. If you have a break, a jump in the graph, it's called the jump discontinuity. You are not continuous. You will not be continuous at A here. The second one,
That will be
and the order doesn't matter with these. You can
infinite.
infinite. An infinite discontinuity is anywhere where your graph has a vertical asymptote. So if your graph takes off to infinity this way, like that, even if this side comes in to a point, and even if it is defined at that point, doesn't matter. If at any point in time the left side or right side go to infinity or negative infinity, this is an infinite discontinuity, because somewhere your function's becoming infinite. And you have to pick up your pencil, right? So we would be discontinuous at A only, right? How about over here? Would I be continuous right here? Sure. I'm saying like forget all this. If I just say, look, in here, from here to here, is the function continuous?
Oh, yeah.
Yeah, because I can draw it and there's no issues. All right, the third and last type of discontinuity, removable. And that's the one that we did just a second ago, like this. It's anywhere where you can easily patch the function so that you can continue to draw it without picking up your pencil. This is discontinuous at A. It is discontinuous, but because I have a simple fix of filling it in if I chose to, it would be removable. So I wouldn't have the discontinuity anymore. All right. Now, I do want everyone to know the definition of continuity. So make sure you kind of burn this into your brain. The definition is the limit as x approaches A of f of x must be equal to f of A. This is the definition of continuity of a function f at A. Please burn that into your brain, because we'll use it quite a bit. It says that in order to be continuous at a point, both the limit must exist, right? The limit must exist from both sides, and whatever the limit is, it must equal the function's value at the point. And again, I went through this in the video.
Which basically all that's saying is that the point is defined.
The point is where you're headed, is what this is saying. Where you're headed from both sides is exactly the point that the function is defined to be at A. All right. Now, examples. I'm going to draw a graph, okay? I'm going to draw a picture for you. And I want us to talk about discontinuities. Let me draw it first, then I'll put the questions up here. Hey, look, my Wi-Fi is better. All right, I'll draw the function in different colors so we can see it. You might take a minute to make sure that if you are writing this down that you have everything correct here. See if there's anything else I want. That should be okay. All right, you ready? I'm going to ask some questions. Where is f, this is the function f, by the way, discontinuous? I messed that up. No, that's right, never mind. Question mark.
We have x equals -1 and x equals
Okay, so anywhere where we see a jump, right? Anywhere we have a hole, anywhere we have an infinite, a function's going infinite.
it's just that one, right? Not the one over by the asymptote.
Pardon me?
Is that part of f as well over there?
This whole thing is f, yeah. So where do we start having these things happen? -3, right? We have a jump. All right, so we'll go through these slowly. At x equals -3, we have a jump, right? We're going to talk about what each one of them are. Jump discontinuity at -3. How about at -2? -2, we have discontinuity, infinite. Because as you come in to -2 from the left, it goes up, right? -1 is removable.
I believe 2 is infinite.
X equals 2 would be our next problem, right? This is removable. And the reason it's removable, it's not a jump because, look, the graph doesn't break and jump, right? Like this one, it broke and it jumped. We jump from here to here. This one, you don't jump, but our hole is not filled in where it needs to be filled in to be continuous. So to fix it, what we could do is we just come in here and we could redefine the function. I could say, hey, look, just at 2 though, instead of being up here at 2 be equal to 1, and then it's fixed. So this is still removable. And anywhere else?
Is that an asymptote?
That is, yeah. I didn't draw the dotted line intentionally because the book doesn't. When you do these problems, they don't draw dotted lines. So you just have to kind of say, yeah, that looks like it's headed to infinity. In fact, they don't even put arrows on it. They just do that. So it's kind of weird, but just please understand they do mean it drops down forever. But this is the way I'll do it on a test. I will draw a dotted line so there's no confusion. Okay, so where else? 3. And this is infinite. Is that all pretty straightforward? Okay, how about this? At each of those discontinuities, I want you to tell me whether or not you're left or right continuous. So let's go to the first discontinuity at -3. At -3, are we left continuous? So as I come in from the left, am I headed to a certain place? I'm not headed to a certain place? I am headed to a certain place, right? I'm headed to 2. But is my function filled in there? It's not. So it is not left continuous. How about at -3 from the right? I'm headed somewhere and it's filled in there. So we do have right continuity at -3. So I'm just going to add that to this. Even though we are discontinuous at -3, we are right continuous there. Right? We are right continuous. We're not. So continuity is a stronger condition than left or right continuity is. Any questions? All right, what about our next discontinuity, -2? Left continuous? It would have to go to a value, right? My function would have to be defined at some point up to, it's infinity. I can't define my function at infinity, or to be infinity, so I can't be left continuous. How about right? Yes. For the same reason it was here. I'm headed somewhere and it's headed to a solid dot. So it is right continuous. I'm just going to put right. Is that okay? Right continuous. How about at -1?
It's removable, yes.
It's removable, but are we left or right continuous? Left continuous?
No.
I'm headed somewhere right, but is it filled in? No, so it's not left continuous. Or right continuous. It's neither. So you don't have to be left or right continuous. It doesn't have to happen. So you can say NA. You can say neither, whichever. Not applicable. I don't like NA. I like neither. Neither makes more sense. The only thing I don't like about neither is the way it's spelled, because it doesn't follow the I before E except after C rule.
The what?
The I before E except after C?
Oh, neither?
English classes?
That wasn't my subject.
It wasn't mine either. That's why I don't like it. I always talk to my classes about this stupid rule. I don't know. I learned it as a rule, I before E except after C.
Yeah.
But it turns out that it's not a rule because it doesn't always apply. So don't call it a rule. So I had a problem with English. All right, X is 2. How about this?
Still neither.
Neither one,
Yeah,
right?
neither.
Neither one. And how about at
On the left.
Neither.
neither? You have to, look, in order for continuity of any kind to happen, you have to be defined at the point you're talking about. So in order for me to ever have any hope of left or right continuity at 3, f of 3 must be defined, and it's not defined. Okay, clear? Okay, I have a question for you. Is f continuous at 0? Yes. Because here's 0, right? You go up to the function, it's there, right? You're going in from the left and from the right. Is it going to the point? Is it filled in? Well, I didn't fill it in for you, right? I didn't put a nice solid dot here for you, but it's implied that that is a dot right there, right? So it is continuous there. Yes. Okay. I'm curious how comfortable you would be. I asked you here where f was discontinuous. What if I asked you where f was continuous instead? So let me rephrase the question here. Where is f continuous? I'm going to leave those up. Well, I don't need to leave those up. So this ties into what I talk about in the video about being continuous on an interval. You can be continuous at a bunch of points, right? In fact, I know that here's a -3. I know to the left of -3, right? To the left of -3, I should be continuous. And according to the arrow, that means it keeps doing this. So would you agree that everything to the left of 3, I should be continuous? How do I say that? In interval notation. -infinity to -3. Now, do I include -3? No, I do not, because there's a hole, right? So I'm going to put parentheses. Then we're going to union. We use our union symbol. Where's the next interval that we are continuous? All in here, right? From -3 until I get to what? -2? Do I include -3? Yes, because I am left continuous. Sorry. Because I am right continuous, right? All the way up, so I can include -3. Now we run into some issues here. Do you see the issue we just ran into? What is it? What is this interval unioned with this interval? It's the same. It's like there is no break, right? Do y'all see that? But there is. If I didn't write this down, then you would think that there's no problem at -3, right? Do you understand what I'm saying? Yes. So we need to make sure that we let everyone know there is a problem at -3. So what we can do is we can change this to an open interval. The only reason I put the bracket was just to get you to think about the fact that we are right continuous, aren't we? We are right continuous. But if I put the bracket, it's going to imply that we're continuous the whole way through, and we're not. So this we have to do to save ourselves. And in the homework, you'll see me talk about the same thing in one of the problems. All right? We must let everyone know there is a problem at -3. Everywhere else, it's okay. Now this goes all the way up until where? -2. And then I'm going to use parentheses. Union. From what? Here to where? -2 to -1. And I'm going to use parentheses the whole way. So in other words, I'm throwing out everything about what's happening at the points. I'm just throwing it out. Because those are problem points. I can't include them in my interval. And I just keep doing this the whole way, right? So next one would be what? -1 to 2. And then the last one. 2 to 3. And it doesn't look like, there's no more picture over here, so I'm not going to assume there is. That would be it. That's where f is continuous. Yes?
Would we have to ever graph the interval?
Graph it? What do you mean graph it?
Like, will they ever give us just that, those intervals, and like graph these?
No, like graph a function that's continuous here? No, no. But that, you could do that pretty easily, because all you'd have to do is like, look, like this, you could make a hole, and then make a hole, and then make a hole, and make, at every one of these little intervals, just make holes at all these places, and you'd be done.
There's no way to know that it's solid that.
You don't know any of that, that's right. Okay, moving along. That's kind of reading a graph, right? I give you a graph and I ask you about continuity. About continuity. And now let's try something more complicated. I don't remember which ones I did on the homework. So I'm going to take a guess here that I didn't do this one. I'm going to do number 16. I have a function f of x equals, I don't remember doing this, so 1 over x plus 2, and then 1 if x is not -2, and if x is -2. All right, so now we're doing something different than what we were doing before. We're going to talk about continuity, but instead of me drawing a picture and asking you, I'm going to define a function. And from college algebra, this is known as a piecewise function, which means that it's defined to be something on a certain part of the domain and something else on a different part of the domain. So let me start by trying to draw this for us. The drawing is just to help us. What for sure do you know? If x is -2, we're at 1. I know for sure that dot is in my picture, right? That's this right here. If x is -2, we're just 1. Now, if you're not -2, that means everywhere else, you look like this, right? And that you would have to go back to college algebra and you'd have to think about, what that looks like and graph it. You would have a problem where? If I tried to graph this, where would I have a problem? -2. And that would actually create a vertical asymptote, because that's where your denominator is 0. So if I were graphing that top piece, I'm going to graph it in red, I know that I would have a vertical asymptote. Please understand, this red is just a guide for me right now. It's just telling me where I would have a problem. And then what would it be doing? Would you, does anyone have an idea what that looks like? The bottom's a line, but it's not a linear function. Well, you could plug in some points, couldn't you? You could plug in x is 0, get a point. What happens if you start, let's start with x is 0. If x is 0, this is what? 1/2? So I know this point's on the graph. What happens if I pick a bigger x, like x is 10?
It starts getting smaller.
It starts getting smaller, right?
Yeah, I remember.
But it's always positive? Right? 1 over a positive number, 1 over a positive number. So it should go like this. And in fact, if you go and review rational functions, you would figure out that this has a horizontal asymptote of the x-axis. So it does that. And then what would happen as I start to move this way? Like if I put a 1 here, or sorry, -1, what happens? What happens if I do -1 right here? It would be 1, wouldn't it? So I'd actually move up. And if I tried and put like -1.5 in there, it's going to start growing. Okay, so this is not a college algebra course. I'm not going to go through the whole technique of graphing a rational function, but that's what it would be. All right? Then if you did the other side and picked some test points, you would determine that it does the same thing but negative. So it does that. All right, so there's our picture. The question is, explain why the function is discontinuous at the given number and sketch the graph. So the given number here, by the way, they say a is equal to -2. All right, they want to know why is it discontinuous here. So can someone tell me why it's discontinuous? It is obviously discontinuous, right? Because that's, so this is an infinite discontinuity, right? We have an infinite discontinuity at -2. So that would be the explanation. Explain.
Put that one phrase.
Yep. We have an infinite discontinuity. I'm going to put dis. Is that all right? Discontinuity. Oh, all right. I won't be lazy. Discontinuity at -2. Right? That's the explanation. We have an infinite discontinuity. And there's our graph. However, I would like to try and answer this question without the graph. Okay? Can I try that? Let's act like I didn't have the graph. And this is where we're going to go back to the definition of continuity to do this. Right? So everyone clear that this is the explanation with the graph, and now we try it without. So acting like we don't know this, I can say for continuity at x equals -2, we need the following. The limit as x approaches -2 of the function to be equal to f of -2. That is the definition of continuity at a point, at the point A, where A is -2. Notice I replaced A with -2 here and A with -2 here, right? That's what I would need, right? To say that this function is continuous at -2, I would need this to be true, right? What is the right side of this equation equal to? What is this equal to? What's f of -2? Plug in -2, you get 1, right? So I know the right side of this equation is 1. And what I'm doing is I'm working the left and right hand sides down together like this, and I'm seeing if they are equal or not. Okay? What is the left side? Well, it's a limit, right? But what function are you actually taking the limit of? It's that function up there, right? But there's two pieces on this function. Which piece are we actually taking the limit of? The top piece or the bottom piece? Top piece. Why? It's heading towards -2, right? Which means you're not -2. Getting closer to -2 without being there. And this is saying, hey, look, if you're not -2, this is what you are. If you are -2, this is you. This is what you are. So since it's a limit, this left side, this function right here, gets replaced with 1 over x plus 2. And now the question that we're asking is, are these the same? Are these equal? Well, let's try the direct substitution in here, direct replacement. If x goes to -2, what happens? We get 1 over 0. And does that equal 1? No, this is not going to happen, right? So we have a discontinuity. We would need these two to be the same. Now, I have to put a little asterisk here because the reason why we stopped here is because we got 1 over 0. And we've talked about, we haven't dealt with this yet, have we? We've dealt with 0 over 0, but not 1 over 0. For right now, just for today and for maybe next class, no, next class we will resolve this actually. On Wednesday we are going to resolve the 1 over 0, all right? But for now, we're just going to say does not exist. This limit doesn't exist. And of course, if this limit doesn't exist, then this right here, 1 is not equal to does not exist. So, that okay?
Is it only if it's 1 over 0?
Any number over 0, other than 0 over 0. So any fixed number that's non-zero over 0. What? This right here are not equal. So, see, in order to be continuous, these would have to be equal. Since they're not equal, it's